Hello friends, welcome to this next video on fixed point iteration method. Like in bisection method, in this video we will discuss about number of iterations required for fixed point iteration method. So in the last video we have discussed about a theorem. So let us just summarize what we have discussed already. We had discussed that this is our problem, f of x is equal to 0. We want to find out a root of this. We converted this into x is equal to g of x. Somehow we have converted this root finding problem into a fixed point finding problem. And then we had seen that if g is continuous on an interval ab and g of x is between a and b for all x in ab, and third one was g dash x is strictly less than 1, then we prove that there exists a unique fixed point of g in the interval ab, and this fixed point was the root of f of x. Further, for any p naught in the interval ab, if you generate a sequence p naught, then p1 is equal to g of p naught, p2 is equal to g of p1, p3 is equal to g of p2, and so on. Pn is equal to g of pn minus 1, then this sequence converges to p, which is the unique fixed point. Call it p, unique fixed point p of g. Okay, so this was a theorem, so it can come in parts. For example, you may be asked to just prove this part of the theorem if you're sitting for some examination, or you may be asked to prove only this part of the theorem, provided the above three conditions are satisfied. And there is a more part to this theorem. Further, if g dash x, you are saying it is less than 1, so for example, if it is less than equal to k, where k is strictly less than 1, then we have these results, the following results. One is pn minus p, that is error at nth iteration, is less than is equal to k raised to power n maximum of p naught minus a b minus p naught. This is one result. And we also have pn minus p is less than is equal to k raised to power n 1 minus k into p1 minus p naught, where p naught is the initial guess and p1 is the next iteration of the fixed point iteration. So today we are going to prove this part and this part. This is what we had done in the last video. From there you can have an idea how to prove this part and this part. So let us prove this thing. So in the last video I am going to prove the first part. I'll start again, otherwise some part of it I have already proved in the last video. So basically I want this pn minus p. Okay, so what I will do, I will write pn as g of pn minus 1, and I will write p as g of p. Why? Because this is how we are generating our sequence. So in place of pn I can write g of pn minus 1, and p is the fixed point, so p is equal to gp. So this is what I have written, and after that I will apply mean value theorem. What is your mean value theorem? Mean value theorem says that g of pn minus 1 minus g of p upon pn minus 1 minus p is equal to g dash c, where C is between Pn minus 1 and P is between Pn minus 1 and P, and this is given to be less than equal to K. So you have G of Pn minus 1 minus Gp is less than is equal to K into Pn minus 1 minus P. So this thing can be replaced as less than equal to K into Pn minus 1 minus P. So you get this result. Pn minus P is less than is equal to K into Pn minus 1 minus P. So we can, here I have started with Pn and P. I can also start with Pn minus 1 minus P is less than is equal to K into Pn minus 2 minus P. Similarly, you can write. And similarly further, you can start with Pn minus 2. So this is less than is equal to K into Pn minus 3 minus P. Then Pn minus 3 minus P is less than is equal to K into Pn minus 4 minus P, and so on. So ultimately you will have P1 minus P less than is equal to K into P0 minus P. So what you can do, you can multiply all these. Multiply them, you will get, see, this term and this term same. You can multiply, and these are inequalities, but everything involved is positive. Left hand side is positive, right hand side positive. So there is no problem in multiplication, for one thing. And also when you multiply, you see left hand side you will get this factor, and the same factor is here on the right hand side. So these two factors will cancel. Similarly, left hand side you will have this factor, right hand side you will have this factor. So these two factors will cancel, and so on. This also, this, and so on. These factors will cancel, and you have K from, you are starting from 0 and you are going to n minus 1. So these are n Ks. So ultimately left hand side you will be left with only this term, right hand side you will have these n Ks and only this term. So it implies you will get Pn minus P is less than is equal to K raised to power n P0 minus P. Okay. Now we want to prove, now you want to prove here left hand side is okay, right hand side you want to prove K raised to power n maximum of B minus P0, then P0 minus A. So this is what you want on the right hand side. So let us look at what is this. What is this P0 minus B? Where these points are? We have started with the interval AB. Both P0 and P are in the interval AB. Why? Because this is what we are talking about. P0 we have started the initial guess in the interval AB, and P we are claiming there exists a unique fixed point in the interval AB. So both these numbers are in AB. So you have this situation. This is your A, this is your B, and somewhere here is your P0. We don't know where P is. Okay, P is anywhere. Now, if this is your B minus P0, and this is your P0 minus A. We don't know, because here I have drawn P0, it may be here also. So whatever is maximum out of these two, what is the maximum out of these two? P is going to be here, here, somewhere in between. So distance between P and P0 cannot be more than the maximum of these two numbers. Right? Is that thing clear? Because you have P0 here. What you are doing, you are measuring the distance from A and P0, and then P0 and B, and then you are taking the maximum of these two. So that quantity cannot be less than the distance between P0 and P. So for sure this distance between P0 and P is less than is equal to maximum of this number, which is B minus P0, and this number, which is P0 minus A. So this is pretty simple. So we have proved that Pn minus P is less than is equal to K raised to power n P0 minus P. So this is the first relation which tells you that error at nth step in case of a fixed point iteration method is less than is equal to K raised to power n, and here you have written here you have to write maximum of B minus P0 and A minus P0 minus A. Okay. Now can you from this relation can you see if K is smaller? For example, if I give you two G's, one G and this is G1, another is G2, for the same function f of x is equal to 0, you can make two different G's, right? and here your all the conditions are satisfied, that your g1 is continuous, it is between the interval a and b, and then you have g1 dash x less than 0.5 here, and here suppose first condition okay, second okay, and g dash x is less than 0.4. If you know this information, then which of the g which you will choose, whether g1 or g2? Because here see, the value of k is less here, it means that error will be less, because error is directly proportional to k raised to power n. So when you have two choices of g, the g with the lesser value of k will be chosen to have less error. It means that it will be converging to your root in less number of iterations. So that you get from this result, right? So this is the first result. Now we want to prove the second result. So let us look at the second result. What we are looking for, we want to prove that Pn minus P is less than is equal to k raised to power n 1 minus k P1 minus P0. So this is what you want to prove. See, I will just tell you the steps, that this is how you have to prove. But this question always comes in the mind of students, that why we have to follow a particular scheme to give a proof for a theorem. So the thing is, when somebody proves a result, for example, some researcher doing research, he is spending many days or maybe months or years to come up with a particular result. So he may have tried many steps wrongly. He may have tried many wrong approaches. And on his lucky day, he comes up with a proper sequence of steps that gives you the proof. Because when he is he's coming up with some result, he is not sure whether this is actually true or not. He come up with result after observing some experiments or something like that, and then he give a proof, formal proof of for this. So whatever steps I am telling you, that are just given by somebody, and maybe to prove the same theorem there may be another path also, that also can be followed. So the main question which comes in the student's mind, that how do we know that these are the steps to approach to this result? So that answer is that you have to just go for the sequence. Maybe there exists another sequence to prove the same result, but there is no method to explain why we are following this sequence. There can be an analytical thinking, that why we are moving from step this to this, but otherwise there is no hard and fast rules that from step this to this you have to move like that. Okay, so see here, this is what we want to prove. So how do we start? See, in the last proof, here we had P0 minus P, and here we have completely different things. Here we have P1 P0, and here we have Pn and P, right? So what I am doing here is, I'll just start with Pn plus 1 minus Pn. Okay, so whatever I have done in the last proof here, see here I have written it as g of Pn minus 1 minus gp. Here, because I am starting with Pn plus 1 and Pn, so I'll write it as g of Pn, and Pn I will write as g of Pn minus 1. So again I'll apply the fixed point mean value theorem. You'll get g dash c, say, into Pn minus 1, right? Now because this is less than is equal to k, so you have this is less than equal to k Pn minus 1. So you get Pn plus 1 minus Pn is less than is equal to this, right? This like this you get it. Now if I apply it to, say, Pn and Pn minus 1, then here you had n plus 1 and n, you get one factor less. Here also you'll get k into Pn minus 1 minus Pn minus 2, and similarly Pn minus 1 minus Pn minus 2, you will get less than is equal to k into Pn minus 2 minus Pn minus 3 and so on. Right hand side I want P1 minus P naught. So I'll stop at P1 minus P naught. So left hand side I'll get P2 minus P1, and before that I'll get P3 minus P2 less than is equal to K into P2 minus P1. So you multiply all these. When you multiply, what you'll get, see, these two factors will cancel. These two factors will cancel. So on the left hand side you will be left with Pn plus 1 minus Pn, and on the right hand side you will have k raised to power n and only this factor P1 minus P naught. Okay, so call it star. Now what I am doing is, let m and n are two integers, and I am starting with, and you suppose m is greater than n may be greater than m also. So if whatever number is more, I am writing that as, you will write it as, you just subtract m minus 1, add m minus 1, pm minus 1, then you subtract pm minus 2, add pm minus 2, and so on. In the end you have minus pn, you add here pn plus 1 and subtract pn plus 1 and so on, right? So you make like these brackets. Okay, here will be minus pm minus 2, okay, sorry, pm minus 3 and so on. Here you will have pn plus 2. So now you have these brackets. You apply triangular inequality. Here you apply triangular inequality. What is triangular inequality? It says that a plus b plus c and so on is less than is equal to mod a plus mod b plus mod c. Here you have a, b, c, d and so on. So this is less than is equal to pm minus 1 plus pm minus 1 minus pm minus 2 plus pm minus 2 minus pm minus 3 and so on, plus pn plus 2 minus pn plus 1 plus pn plus 1 minus pn. Okay, now go to star. Here star says the difference between two consecutive pn and pn plus 1 is less than is equal to k raised to power n. Whatever is a factor here in the second term will come here, and with that you have p1 minus p1. So here you have m minus 1. So you will get this using star. The first quantity, this quantity is less than is equal to k raised to power m minus 1 into p1 minus p naught. The second quantity is less than is equal to k raised to power m minus 2, whatever is here, into p1 minus p naught, plus this is so on. Last term is k raised to power n p1 minus p naught. Now you see here this term k raised to power n and p1 minus p naught is common. So take it out. So k raised to power n p1 minus p naught common. Inside you will have 1 here. I am writing in the reverse way, and then k, before that you had k raised to power n plus 1 p1 minus p naught, this term. So it will be k square and so on, and here you will have k raised to power m minus n minus 1 because you have taken k raised to power n common. So this is what you get, right? But I want to have on the left hand side, I want to have pn minus p. So pn is here. I want to get rid of this m, and also I know that the sequence pm is converging to p, because that is in the first part of the theorem, that the sequence generated is converging to p. The subscript doesn't matter, it can be pm or pn, whatever, it is just a dummy number. So I can take limit m going to infinity. So you will have limit m going to infinity. Actually this was outside, but I am taking it inside. You can bring it inside, and there is no m here, so no limit. Less than is equal to, here is no m, here is no m. So you have k raised to power n p1 minus p naught limit m going to infinity 1 plus k square and so on plus k raised to power m minus n minus 1. So this is equal to k raised to power n p1 minus p naught. This becomes, because m is going to infinity, so you have 1 plus k square up to infinity, and left hand side is your, this is p because pm sequence converges to p. So this becomes p minus pn. Now tell me, what is this? This is a GP, geometric progression, with common ratio k which is less than 1. Therefore its sum is a first term upon 1 minus k common ratio. So you get p minus pn is less than is equal to k raised to power n into 1 minus k into p1 minus p naught. So left hand side you can write it as p n minus p, because it is modulus, doesn't matter. So this is the result which you wanted to prove, right? So this is these two videos, basically the first video on the fixed point iteration method and this video, they both are telling you the technique, how to apply a fixed point iteration method and what is the error analysis. So in the next videos we will practice the questions so that we can have knowledge how to use these two videos, right? So that we will do in the next video.